Hi there, and welcome to Chapter 2, called The Chemistry of Life. In this chapter, we're going to discuss the building blocks of cells, which are molecules, and we're going to discuss what molecules are made of, which is atoms. After today's lecture, you should have a better understanding of atoms and what they're made of, as well as ions and isotopes in relation to biochemistry. You should also have an understanding of molecules, what they are made of and what they make up, as well as how hydrogen bonds give water its unique properties. And there are a handful of very unique properties that ultimately allow for there to be life on this planet, and it's all due to water's really awesome properties. And the last takeaway point today is how water ionizes, which is how it breaks apart into its atoms that it's composed of, which are hydrogen and hydroxide, or OH. And we'll also talk a little bit about the pH scale. So although you're taking a course called Concepts of Biology, it would be difficult to understand the very tiny aspects of biological processes if you also didn't have an understanding of some basic chemistry. So the marriage of the two subjects there is what we refer to as biochemistry. And so any substance in the universe that has mass, like you, and occupies space, like you, is comprised of matter. All matter is made up of atoms. So you are made up of atoms, as well as the chair that you're sitting on is made up of atoms, as well as the food you eat, as well as every living thing, down to bacteria, including non-living things like air and rocks and everything. Atoms have a pretty basic structure. They all have the same structure. So, like you may know about cells, nuclei, atoms also have nuclei. But the atomic nuclei are composed of protons, very tiny subatomic particles that have a positive charge, as well as neutrons, so think neutral and no charge. Circling and buzzing around the nucleus are even tinier particles called electrons, and so think that they are negatively charged. A visual representation of our basic definition of an atom is shown to you here. So on the left you have a hydrogen atom, and hydrogen, if you look at the periodic table, has only one proton in its nucleus. And so this, as other atoms, are neutrally charged unless they are an ion. So this hydrogen atom has a positively charged proton in its nucleus and one electron in orbit around its nucleus. So a positive plus a negative charge neutralizes out, so no charge. And if you look at carbon over on the right, this carbon atom is also neutrally charged. There are a couple of ways that we can quantify atoms in numerical ways. One of them is the atomic number, which is the number of protons that an atom has in its nucleus. So atoms with the same atomic number will behave similarly in a chemical manner. So that would be, they would belong to the same element. Whereas the mass number of an atom is the number of protons and its neutrons in the nucleus. The reason we don't count electrons in the mass number is because they have such negligible or almost indistinguishable mass. Electrons are really important, however, in the sense that they determine how a particular atom is going to behave. And I'll show you here in the next few slides what I mean by that. Electrons are super important because they have something called potential energy. And so like I said earlier, they buzz around the nucleus of the atom and they carry energy for that particular atom. They can be associated in one of several different orbitals or spherical rings around an atom. The reason that electrons and electron shells is so important for an atom is because the more incomplete an electron shell is in a particular atom, the more likely it is that that atom is going to be reactive. And when I say reactive, I mean the ability that that atom has to bond with another atom, ergo forming a molecule. So it's a little bit more interesting for us in biology and chemistry in relation to electrons is that when atoms gain or lose one or more electrons, we actually call them an ion. So like I mentioned earlier with water breaking down into hydrogen ions and hydroxide ions, what's happening is that electrons are being gained and lost. Another interesting concept is that of isotopes. Atoms that have the same number of protons but different numbers of neutrons in their nuclei are considered isotopes of an element. And what's interesting, especially in biology and something we call carbon dating, is that we can determine how old something is based on how much its nucleus has actually decayed over the millennia. And what we look at are different isotopes of carbon in order to determine this. Here's three of the really common, two isotopes of carbon, and then on the far left you see regular stable carbon. So what will happen though is that it will decay or degrade over time, and that's how we can use radioactive dating to determine the age of something really ancient. If we take this knowledge of atoms and how atoms can lose and gain electrons, they can actually share electrons, or they can kind of be close to other electrons and other atoms, and thus form molecules. So all a molecule is a group of atoms that's held together by some form of a chemical bond. The three types are ionic, covalent, which are really strong, and hydrogen bonds, which are pretty weak. Van der Waals forces are basically a kind of weak chemical attraction. They're not considered a bond, but it's what happens when atoms are kind of in the vicinity of each other, but they're not actually sharing electrons, and there's no actual bond between those substances. A great example of an ionic bond is the attraction that Na, or sodium, and Cl, or chlorine, have to each other, forming an NaCl molecule, which we know that commonly as table salt. So what they actually form are stable crystals. Covalent bonds are actually the strongest of the bonds that we're going to talk about together, and covalent bonds are going to be coming into play in some of the later chapters when we start talking about the structure of DNA and the types of bonds that hold it together. So in covalent bonds, electrons are actually shared between two different atoms, so making a really strong bond. Here's a great example of some covalent bonding. On the left, you can see two hydrogen atoms that are covalently bonded with each other to form hydrogen gas, or H subscript 2. On the left, you can see more of a space-filling electron orbital sharing model, where you can see they've actually drawn in for you the two different, right here, the two different electrons right there and there that are actually equally shared by this hydrogen ion and then the hydrogen ion on the right. A special type of covalent bond, and a really important one, especially on our planet Earth, because it allows us to have water, liquid water, I should say, liquid H2O, is something called a polar covalent bond. And these bonds form between the oxygen and the hydrogens that make up a water molecule. They're really strong, but water is a polar molecule because it is slightly electronegatively charged on where its oxygen ion is positioned in the molecule. Our last type of official bond that we're going to talk about is hydrogen. Hydrogen bonds don't share electrons. They are simply weak electrical attractions between the positive end of a polar molecule and the negative end of another. And so a great example of this we can actually also see in water molecules, which we'll show on the next slide. So what we've got here is a nice space-filling model of one water molecule hydrogen bonding to another water molecule, and what holds each individual water molecule together are actually those polar covalent bonds. So we've got a great example here of two of our bonds that we're going to talk a bit about in our class. So like I was saying earlier, it is very essential for life on Earth that we have liquid water. And what we're going to talk about are the unique properties of water that actually allow it to exist in a liquid, a gaseous, and a solid state. And so water is essential for life. It is a polar molecule, and we already talked about the two kind of bonds that it can form. And so we're going to take that knowledge and apply it to the other unique properties of water. Water is a great storer of heat. So if you think about something called the lake effect, being from the Midwest, we would always hear about the lake effect happening in Lake Michigan down by Milwaukee and Chicago. And usually temperatures near the lake will be more mild than they are inland, because water can retain heat over a period of time, and so it's not going to lose that heat as quickly as the air and the climates more inland. Water also has this awesome ability to form ice. So few of its hydrogen bonds break at low temperatures, meaning it actually is going to expand and stabilize and keep those water molecules far apart from each other, but still hydrogen bonded. And then the high heat of vaporization that water has is really interesting because water requires a lot of energy to actually go from a liquid to a gaseous state, because a lot of hydrogen bonds must be broken, and it takes a lot of energy to break those bonds apart. Here's a great drawing of what ice actually looks like molecularly. So on the right here, we have really spaced out water molecules, spaced out from each other, connected by these nice hydrogen bonds. And you can see there's a lot more hydrogen bonds in this picture on the right than over here in liquid water. So liquid water is liquid and less stable and solid than frozen water, because it has actually less hydrogen bonds holding those water molecules to each other. And this is a property that we call cohesion, the ability of water molecules to bond with each other. Think co like cooperate, or community. So cohesion actually allows this little insect to be able to stride or appear to walk on the water. Another great property of water is that it can adhere to substances that you put it in. So if you ever pour water into a glass or even a container with a tiny diameter, you'll see that the water almost begins to creep up the side of that container, and that's because water can adhere to that substance. Like we mentioned earlier, water is very polar, and certain molecules like water and they dissolve easily in it. We call those molecules hydrophilic. Hydro meaning water, and philic or philos meaning loving. The opposite of those molecules are hydrophobic ones. Phobic, like phobia or fearing, they are repelled by water because they are nonpolar and they don't dissolve easily in water. An example of that would be oil. Water can actually be broken up into two ions. So when water dissociates, or when that covalent bonding holding the water molecule together is broken apart, water will actually break down from H2O, meaning two hydrogen atoms and one oxygen atom, into a hydroxide ion, because now it has that charge there, and a hydrogen ion because it's got that charge on the hydrogen atom. And how this relates to your daily life is that we can actually look at ionized hydrogen and how much of it is in a substance to determine what its pH is. So here's a scale you may have seen before. It's called the pH scale. And what pH is the negative log of the concentration of hydrogen ions in a substance. So the more acidic a substance, the smaller pH value that item will have, so closer to 0. 7 would be neutral pH, so that is pure water. Notice that blood is almost neutral. The more basic, or the less hydrogen ions, the more hydroxide ions that a substance has, the more basic it will be and the larger the number. And here's a great breakdown of acids and bases and what their numeric values are on the pH scale. So I hope that was helpful, and please stay tuned for the next video on Chapter 3, Macromolecules. Thank you.